So in this media, we are going to discuss about synchronous rolling and parametric rolling of the ship. So see, I have taken exactly the extract from a book, okay, and just go through it. It is in a very simple, crisp and lucid manner. It is described over here, and I keep on saying in my videos that my intention is not to teach you. I'm not at all a teacher. My intention is to bring the content under one umbrella. What are the questions of the surveyor and what is the expected answer, so it becomes handy and easy for you to refer to it. So that is the whole idea altogether. So now when we speak about synchronous rolling of the ship, synchronous rolling is caused by the ship's rolling period, that is TR. Now here we are denoting the rolling period as TR. Now this TR becoming synchronous or resonant with the wave period. So when this rolling period is becoming synchronous or resonant with the wave period, then it is causing this synchronous rolling. When this occurs, the ship will heel over. So now when this condition is met, what condition? That the rolling period is becoming synchronous or resonant with the wave period. When this occurs, the ship will heel over and in exceptional circumstances be rolled further over by the action of the wave, and it will be rolled further over by the action of the wave. Consequently, there is a serious danger that the vessel will heel beyond a point or angle of the heel from which it cannot return to upright condition. Now there will be a condition and there will be a situation wherein the ship will continue to move in that fashion only, in that heeled condition only, with that heel angle only, and it will not be able to, no external force can bring it back to its upright position condition. The ship ends up having negative stability. So you must have studied this ZZ curve and all. I hope it is known to you. So there you will have this negative stability. So this area and will capsize. We'll show you the figure. This figure show as a ship with synchronous rolling problems. So this will have synchronous rolling problem. Now what is the whole idea altogether? See, synchronous rolling in waves. So now see, ship rolls to port. Okay, port direction. Wave direction is this. Now wave. Now the crest wave, it is coming at the trough, and the trough wave. Okay, so direction of rolling, it will come and roll in this direction. Ship rolls to starboard. Now first ship becoming upright, and then ship again going to the wave direction. Now how we can reduce this synchronous rolling? Use water ballast changes to alter the kg of the ship. Okay, use ballast changes to alter the kg of the ship. This should alter the GMT. Okay, now the GM is, that is your metacentric height. Okay, now this is transverse metacentric height, and hence the natural rolling period TR to a non-synchronous value. So it will come to a non-synchronous value, that is your rolling period, that is denoted by TR. Change the course heading of the ship so that there will be a change in the approaching wave frequency. So we are supposed to change the course heading of the ship so that there will be a change in the approaching wave frequencies. In other words, introduce a yawing effect. So what we are supposed to do is we are supposed to introduce a yawing effect. Alter the Now what we are supposed to do is alter the ship's speed until synchronism or resonance no longer exist with the wave frequency. So we can again have a look at this diagram. Just pause for a minute. Okay, so I hope it is clear for you. Now this what we discussed, just have a look at it. This, so we are introducing a yawing effect. So yawing effect on a ship refers to the rotational motion around its vertical axis, causing the ship to swing from side to side. It's one of the 6 degrees of freedom of a ship's motion at sea, alongside heaving, swaying, surging, rolling and pitching. Yawing is a result of wave action, wind and current, and can affect the ship's stability and maneuverability. Okay, so it will reduce your stability of the ship, and then maneuverability issue and increased side forces. That will also have influence on cargoes altogether. Now When we come to this parametric rolling of the ship, parametric rolling is produced by pitching motion on vessel that have very fine bow lines together, okay, with very wide and full stern contours. One such ship type is the container ship. Now we'll see the diagram. Shows a ship with parametric rolling problem. So container ship will generally have this effect of this parametric rolling condition. The cause depends very much on the parameters of the vessel, hence the main parametric rolling. It is most marked when the pitching period, that is TP. Now there we describe this rolling period as TR. Here we have pitching period, that is TP, is either equal or half that of the vessel's rolling period, that is TR. It is generally half. Now TP can be equal or it is generally half of that of the vessel's rolling period. Okay, as the stern dips, now the stern part of the vessel dips into the wave, it produces a rolling action. So it will have a rolling action which remains unchecked as the bow next dips into the wave due to pitching forces. It is worst when TP is equal to TR. When your pitching period becomes equal to that rolling period, this condition, this is very significant. So you have to remember it not only in as per exam point of view, also as per your stability point of view, or when TP is equal to half into TR. Now, in effect, the rolling characteristics are different at the stern to those at the bow. This causes a twisting or tossing alongside the ship, leading to extra rolling motion. So now this is leading to the extra rolling motion. See, because what will happen in loaded condition and in not loaded condition, now the ship's engine room is generally in the aft side. Okay, so when you have ship's engine room in the aft side, some of the container ship they have in the midship as your bridge in the midship also all together. Generally we are, so the term of the rolling condition, when it is loaded, the stern will have different dip and the surging period, or when it is dipping and when it is coming out in comparison to the aft. So because of which, because of this difference in the characteristic in the stern and the bow, there will be a twisting and torsioning alongside the ship. So this will lead to extra rolling motion. Now if TP is equal to TR or TP is equal to half of the TR, then interaction exists and the rolling of the ship is increased. Now this will increase your rolling of the ship. A more dangerous situation develops because of interplay between the pitching and the rolling motion. Now the diagram that we were speaking about is this. Now you see the vessel. Now this is the rolling motion from port to starboard. Okay, now this is the pitching motion. This is the stern part of the ship. Okay, pitching motion that the ship will dip inside and then come out. Very wide bluff stern. So it will have a very wide bluff stern because of this rolling motion of from the port and starboard. Now this is the pitching motion for the forward. Bow rolling to starboard. Now this bow will roll to starboard. Now hollowed out forward end contours, because it is a streamlined body, very fine bow lines. So we have, this is the diagram that we were speaking about. Now parametric rolling is reversed when the ship is operating at reduced speed in heavy sea condition. So when the sea condition is heavy and the vessel is operating at a very reduced speed, such condition can cause containers to be lost overboard due to broken deck lashings. The IMO suggests that the parametric rolling is particularly dangerous when the wavelength is 1 to 1.5 times the ship length. So wavelength is 1 to 1.5 times the ship length. This condition leads to parametric rolling. Parametric rolling problem are least on box shaped vessels or full form barges where the aft and the forward contours are not too dissimilar. Very little transverse and longitudinal interplay occurs. To reduce parametric rolling, so what are the conditions we saw, that how we can reduce the synchronous rolling and how now we can reduce this parametric rolling. A water ballast could be used to alter the transverse metacentric height and hence the natural rolling period, that is TR, to a non-synchronous value. The ship need to have an anti-rolling acting stabilizing system. Anti-rolling stabilizing tanks that transfer water across the ship or vertically between two tanks are effective for all ship speed. A quick response time is vital to counteract this type of rolling. Hydraulic fin stabilizers would also help to reduce parametric rolling. They may be telescopic or hinged into the sides of the vessel at or near to amidships. Okay, alter the ship's forward speed, alter the ship's course. So these things that we can do. Okay, so I hope it is clear for you that what is parametric rolling and what is your synchronous rolling, and what is the condition and how we can reduce the synchronous rolling and how we can reduce this parametric rolling. What is the condition which is deadly when this TP, your parametric rolling, is equal to this your synchronous rolling, that is synchronous rolling, or that is your, or it is half of the TR. When TP is equal to TR or TP is half of the TR, this condition is very deadly. How we can reduce this? We discussed in about parametric rolling, we have fin stabilizers and all those things. Okay, these ballast tanks, and so this, how, what is your response time, which is very crucial in such case and such rolling period. So these things are few things. You can pause the video and then you can have a look at it all together. So this is the expected answers for the surveyor and what the surveyor is expecting from you. Thank you so much. Thank you for your valuable time. All the very best for your exams.